So, good morning, ladies and gentlemen. Today I'd like to speak to you about a CD test method for evaluating injector nozzle deposit effects in diesel passenger cars. So, thank you. This is work led by myself and my colleague Alistair Smith on behalf of Shell Global Solutions UK. So, brief overview of the presentation. Firstly, an introduction, then why we saw a need for a new test to complement the existing industry standard method, how we established the initial test operating point for the new method, an overview of the method development, the application of the new method to a vehicle fleet test, and a summary. So, direct injection fuel systems dominate modern diesel applications, and when deposits form in the holes of these DI nozzles, we can get reduced injected quantity and impaired spray formation, among other things. And in turn, these can lead to power and fuel efficiency detriments, as well as emissions detriments. So there's an industry standard test for evaluating DI nozzle hole deposits, and this is developed under the auspices of CEC. It's commonly known as the DW10B test, and its focus is to evaluate fuel and additive effects on DI nozzle hole deposits. So the CEC test is engine based. It uses very high loads, and the main metric is power. So the images below show on the left-hand side a nozzle hole from the CEC engine test, which is new and unused, and on the right-hand side a nozzle hole from the CEC test, which is run for 16 hours under the CEC test cycle with a off-specification B7. And the deposits that you can see within the hole led to power loss of about 6%. So why did we foresee a need for a new test to complement the CEC method? Well, the CEC test, as I mentioned, is characterised by having a very high load test cycle, so over half the time is spent at full load, whereas we wanted a test which was lower loads, which would be more realistic of market applications. The CEC test as an engine test is restricted to a single engine type, whereas we wanted something we could apply to vehicles and therefore make it more flexible and less prone to obsolescence, so we can simply update the vehicle types that we use in the test. The CEC test specifies special injector nozzles which are designed to simulate high hydraulic efficiency types, which are fouling sensitive, and we wanted our test to work in standard or modified vehicles from the road. So you know from the literature that nozzle tip temperature is a critical parameter for deposit formation, and typically deposits form more readily at higher nozzle tip temperatures. We also know that the CEC test cycle is good for deposit forming. So to determine a basic operating condition for the vehicle test, we compared nozzle tip temperatures from the CEC test to those that we generated in an experiment with a vehicle where we ran a vehicle with a DW10B engine on a chassis dynamometer over a range of speeds and loads. So the plot showing BMEP versus nozzle tip temperature, the red circles show the CEC test operating points, the black markers are data from the vehicle, and then the different shapes within the vehicle data are different different speed settings. So you can see that load is more important than speed in terms of nozzle tip temperature, and there's three populations indicated in the data by the the blue ellipses. So in the bottom left-hand corner, we've got all the data recorded at lower loads up to and including 60% load. Then towards the top right, we have the 80 and 100% load populations. So you can see that the 80 and 100% load populations are quite close in terms of nozzle tip temperature, where there's some clear separation between those and the 60% load population. And so, as a balance of trying to retain sufficient nozzle tip temperature to have a good fouling rate against trying to avoid very high loads, we adopted the 80% load point as the basis for our vehicle test. I'll just mention the CEC 60% load point in the centre of the plot. That's higher nozzle tip temperature than the equivalent vehicle measurements, because the CEC test specifies no EGR, and EGR is, as we know, reduces combustion temperature, and that is in use in the vehicle calibration at these conditions. So overview of the test method development. So we ran initial tests with 2 Euro 5 vehicles and applied a test cycle which was primarily 80% load and 120 kilometres an hour. We measured full load power at 12-hour intervals to determine deposit formation. And we used the fuel which was mainly comprised of the reference fuel used in the DW10B test, but with 7% volume of off-specification FAME to give some fouling propensity. And in clean-up phases, we added a novel detergent at a premium dose rate. So as you can see from the plots, we did achieve some power loss in the dirty-up phases, and some power recovery. So power loss, dirty-up phases marked in the red markers, I should say, in blue, the clean-up phases. So we achieved some power loss in the dirty-up phase in both vehicles, and some power recovery with the detergent. But these tests were very long in duration, and there was some clear evidence of long-term drift affecting signals in both cases. So from those initial tests, we took some learnings and progressed to an intermediate test method, and one further change to bring us to a finalised test method. So in the original method, we were above road load for almost all the time. So road load, I mean as the load that the engine would experience in the vehicle if it was running at steady speed on a level road. The tests were very long duration, so around the 100 hours mark. We only measured full load power every 12 hours. There was no stabilisation phase included initially, so we allowed a basic engine warm-up of about half an hour before we went straight into the dirty-up phase of the tests. So there was no decoupling of long-term stabilisation from deposit effects. We also stopped the vehicles for engine lubricant top-up, so interrupting the tests there. And we achieved about 3% power loss with off-spec B7 in the long dirty-up duration, so 48 to 72 hours. So from this basis, we ran some tests in an intermediate method. So we reduced the load intensity of the cycle, but still the cycle remained for the vast majority of the time above road load. Reduced the test duration down to 36.5 hours, and increased the full load measurement frequency to twice per hour to give us better resolution on the deposit signal. And we introduced a 12-hour stabilisation phase, which meant running with detergent additive fuels for the first 12 hours of each test. So this allowed us to decouple stabilisation effects of the vehicle, so long-term driveline thermal effects, plus stabilisation of the injectors. So we used new injectors for each test. We introduced a system of continuous engine lubricant top-up, So this was using a peristaltic pump to replenish the oil during the test, so we didn't have to interrupt the tests for lubricant top-up. And we also switched the profiling element of the fuel from the B7, off-spec B7, to 1 ppm of zinc, which is used in the standard CEC test, which resulted in us getting about 3% power loss in the 12-hour reduced dirty up length. So one further change for the finalised method was again to reduce the load intensity of the cycle, so that we brought the time spent above road load to just under half of the cycle time, and this reduced our fouling rates from 3 to 2% power loss in 12 hours. So this plot shows, compares results generated on the intermediate and finalised cycles in vehicle A. So you can see in the dotted line we have intermediate test cycle, in the dashed line power with the finalised cycle. So in the first phase, where we use the detergent, the stabilisation and keep clean phase, you can see by the end of that phase we've got quite a nice steady power signal. Then as we exclude the detergent, deposits form, to a lesser extent with the finalised cycle, which is lower load intensity. And then as we reintroduce the detergent, we recover the power lost in the dirty up phase. So although the change in reducing the load intensity in the final cycle did reduce our signal somewhat, there was still sufficient signal and sufficiently good signal to noise to make that step. So to ensure that what we were measuring was indeed due to nozzle hole deposits, for a couple of experiments we removed injectors from vehicles A and B running on the finalised test cycle after the dirty up phase, and recorded these images, so you can see that indeed deposits are forming in the nozzle holes as power is lost, and these levels are commensurate with what we'd expect for these power loss levels from the CEC test. So then we applied the finalised method to a vehicle fleet. So we selected 7 vehicles representing models from Europe, considered range of vehicle ages in the selection, range of geographical origins, a range of FIE manufacturers, a range of OEMs, and coverage of several vehicle segments. So some details of the fleet. So we've got some coverage of engine displacements, rated power, 6 out of the 7 cars are common rail with 1 unit injector car, and we covered Euro 4 and 5 types. So we plan to do 2 tests on each vehicle. So in the first 2 stages, warm-up and stabilisation, we used B7 plus zinc plus novel detergent, so the detergent in there to prevent any deposit formation during that stage, and therefore allow us to decouple stabilisation from deposit effects. And in both tests we excluded the detergent, and so that deposits could form. And then in the final stage, the clean-up stage, in one test we used the novel detergent in the clean-up stage, and in the other a conventional detergent. Both of these were applied at premium dose rates. So this shows the individual vehicle power loss recorded over dirty up for the 7 vehicles. So you can see vehicle C, there was no power loss recorded in the first test, so we didn't run a second test with that vehicle. But all of the other vehicles did exhibit some power loss due to deposit formation, ranging from 1 to 5%. and we did get quite good repeatability, as you can see, comparing the dirty up in the first and second tests. So this plot shows fleet average power, change in power I should say, for the two tests. So in the blue markers we have the tests where novel detergent was used in the clean-up phase, and in the other, the yellow markers show that the results of the test where conventional detergent was used in the clean-up phase. So you see quite good power stability towards the end of the keep clean or stabilisation phase in both cases, and then good repeatable power loss in the dirty up stage, followed by, in both cases, clean up in the clean up stage, but the novel detergent outperformed the conventional detergent quite substantially. And this plot shows BSFC, change in BSFC over the same format. So there's obviously quite a bit more scatter in the data here, but fairly flat BSFC in the stabilisation phase, followed by increase in BSFC in the dirty up phase as deposits form, and then some recovery of that BSFC increase in the clean up phase. And again, the novel detergent outperformed the conventional detergent. So in summary, we've developed a test method for evaluating DI nozzle hole deposit formation and removal in modern diesel passenger cars at quasi-realistic conditions. And we've applied that method to a fleet of 7 representative vehicles from the European market. And 6 out of the 7 cars accumulated deposits, which was determined through loss of power and increase in fuel consumption. Detergents applied at premium dose rates were effective at controlling deposit formation, and the novel detergent applied outperformed the conventional detergent in recovering power and fuel efficiency lost in all 6 responsive vehicles. Thank you for your attention.